Here we have 2-point charges. We'll call them Q1 and we will call them Q2. And they both give off electric fields. And we've got this point over here, and we're going to find out what the electric field is at that location. So we're going to find out the total electric field here at that random point. So first I'm going to find out my two electric fields for my individual charges. And we'll say this guy right here is 7.6 nanocoulombs. So if we do that, we can use our electric field expression, where our electric field is going to be equal to KQ1 over radius 1 squared, where for the other one, I'll say this guy over here is negative 8.0 nanocoulombs. I'll do the exact same thing over here, or the electric field number 2 is going to be equal to KQ2 over radius 2 squared. So if I first of all calculate my electric field for Q1 using KQ1 over R1 squared, I've got an electric field from the first one of about 3.49 times 10 to the 11 newtons per coulomb. Now this is a positive charge. Now since this is a positive charge, the electric field would radiate out from it. So at this location, it would be going in the upwards direction. So that field is going to be going up. Now I'll do the same type of thing for my other charge. I'll do KQ2 over radius 2 squared using my second radius, my second charge. And I'll do the exact same type of calculation. And I get an electric field of 1.80 times 10 to the 11 newtons per coulomb from that guy. And that electric field is for a negative charge. So for a negative charge, the electric field would be going towards it. So at that location, it'd be going towards the right. So this one would be going towards the right. So I've got my two electric fields. The one from E1 is going up this way, so it's going upwards. And then for my Q2, it's going towards it, so the electric field will be going this way. And there are my two electric fields. Now, all I have to do now is take those two electric fields and make a triangle out of them. So I've got my two electric fields. I'll start with my E2. I've got an electric field of 1.8 going towards the right. And then I've got my second field of about 3.49 going up. And if I put those two together, I get a triangle that looks something like this. Let's use my trig and Pythagoras to figure out my triangle. So if I use my trig and I use my Pythagoras, I find out that my total electric field would be about 3.93 times 10 to the 11 newtons per coulomb. That'd be the magnitude. But then, of course, I also need the direction, and that's the angle here before. And if I use my trig, my angle would be about 63 degrees. And there's the electric field at that location, something like this. Of course, if you would map it out, the electric field between the two charges would look something like that, and this would be tangent to the curve at that location. Now, a really common thing to do now would maybe put a charge there. So let's put an electron there, and if we do that, there will be a force. So let's find out what the electrical force on the electron would be. Now, what you might want to do is use the classic force expression KQQ over R squared, but we don't actually need to do that because we've actually done this part already. That's the electric field. So we can sort of shortcut things a little bit and just jump to calculating the force. I mean, you could calculate force number 1 on the electron and force number 2 on the electron and put the forces together and make a new triangle. But again, a lot of that work has been done with the electric field. So it's a lot easier just to jump to F equals QE and calculate the force that way and use this electric field right there. So if we do that, we can calculate our force to be about 6.3 times 10 to the negative 8 newtons on the electron. Now, of course, we also need direction. Now, since it's a negative charge, it'll go the opposite direction of the electric field. So if the electric field is going upright, our electron is going to go down left. So I have to add 180 degrees to my 63. So my electron would experience a force at approximately 243 degrees and go the exact opposite direction of the electric field, which sort of makes sense because it would be attracted to the positive charge and repelled from the negative and would travel around something like that.